Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the same. Excess of isobutane on reaction with the bromine molecule in presence of light at 125 degrees Celsius gives which one of the following as major product? So we have described a reaction here in the question that when you take isobutane in excess and you react it with the bromine molecule in presence of light at 125 degrees Celsius, so these are the conditions of the reaction. You have to tell that from the options, from the given options, which one will be formed as a major product. Options are, you can see in the A option we have bromine at the second position and also methyl as a side group on the second position, and we have a chain of propane or propyl. Also one bromine is at the end or third carbon. In the B option we have this similar kind of structure, two bromines are present, but at the second position methyl bromide is present, and at the third carbon we have one bromine. In the third option we have only single bromine in the structure which is attached to the third carbon, and one methyl chain is attached to the second carbon. In the D option we have one bromine attached to the second carbon and two methyl groups as a side chain are attached with the second carbon. So these are the structures, and you have to find out that after observing the reactions, after observing the reaction which is explained in the question, what will be the major product. So for the given question, the correct answer is option D. Using the concept 15.34, excess of isobutane reacts with the bromine molecule in presence of light at 125 degrees Celsius, which will give 2-bromo 2-methyl propane as a major product via free radical halogenation reaction. So, as asked in the question, that when excess of isobutane react with bromine, what will be the major product? So when excess of isobutane react with bromine, so we get the product as 2-bromo 2-methyl propane, and this reaction has happened by free radical halogenation reaction. You can see that there is a isobutane molecule, right? Isobutane means methyl chain is attached to the second carbon in the propyl, in the propane chain. Okay, so we have isobutane in excess amount. We are reacting it with the bromine and in presence of light and at 125 degrees Celsius. It is forming a structure like this, which is 2-bromo 2-methyl propane, because at the second carbon we have bromine, at the second carbon we have methyl. So it is 2-bromo 2-methyl propane structure. If you talk about the mechanism, this above reaction is halogenation of what? Alkane. This the reactant is alkane we have, and we are doing halogenation of alkane via free radical substitution reaction. So this will be the mechanism. So initiation, it involves 3 steps: initiation step, propagation step, and finally termination step. So in that initiation step, what will happen? The bromine will break into the free radicals, two free radicals of bromine in the presence of light. In the propagation step, the we take the reactant, which is our alkane. which is isobutane. So we take the isobutane and we react it with one of the free radical of bromine. What will happen? This free radical will take this hydrogen of one of the carbon, or you can say second carbon, which is most acidic in this structure, and this free radical structure of this isobutane will form. So this free radical, so this at the carbon this dot will come, because from here we have snatched the hydrogen, and the HBr molecule is formed. And as you know that the isobutane are in excess amount, so again this free radical will react with the bromine molecule and it will form CH3C, CH3, CH3Br. Okay, at the second position bromine will attach, and bromine will again go to the free radical, right? So this structure will form. Now finally there will be some ending of this process, so the termination step will happen. And in the termination step, these two free radical which we obtain first is here, and initially we have one remaining, right? These two combine together and form a bromine molecule, and then one of the bromine radical reacts with this one of the you have butyl free radical, so react with this butyl free radical and form this major product as 2 bromo 2 methyl propane, right? So finally in the termination step we got this major product 2 bromo 2 methyl propane in the termination step, right? So this is the whole mechanism of this reaction which is given in our question, and hence the correct answer is option D. Let's move on to the next one. The number of optically active products obtained from the complete ozonolysis of the given compound is. So we have given a compound here. You can see the structure. We have a long carbon chain in which 3 double bonds are present between 2 carbons, and one there is a this structure is 3D structure. So basically you can say this is spatial arrangement of methyl at the 2 carbons, right? In the first one it is outward the plane, and the second it was inward the plane, the methyl position, right? And the hydrogen position is also vice versa. So this is the structure, and we have asked that when you do the complete ozonolysis of this given reaction, of this given compound, what will be the number of optically active products which you obtained? So the options are 0, 1, 2, or 4. So for the given question with the given compound image, we have the correct answer as option A, which is 0. So using concept 15.1, ozonolysis of given triene. Why we are calling it triene? Because there are 3 number of double bonds present, and we represent double bond as alkenes compound, so that is why we are calling it as triene. So when you do the ozonolysis of this triene, it will occur as follows. So we take this initial compound given, we do the ozonolysis of this in presence of zinc or water. What it will form? It will break. It will break from the double bonds, and it will form 2 molecules of this ethyl aldehyde, and this 2 molecules of C CH3H CHO CH. 2 groups of aldehyde is attached to the second carbon, and one methyl group outwards the plane and one hydrogen inwards the plane, right? So these are the 2 compounds we obtain after the ozonolysis of the given compound, and this is how it will happen. Since none of the above products is chiral, no optically active product is obtained. So we have to find out that in the product what is the number of optically active compound we get. Okay, so if you see the products, there are two molecules of this one and two molecules of this one, but in the two molecules of ethyl aldehyde you can see none of the one is chiral. In the other two molecules we obtain as a product, there are also no number of chiral compounds present, right? Hence, there will be no optically active product we obtained after the ozonolysis of given compound, and thus we have our correct answer as option A, that is 0. Okay, let's move on to the next one. CH3 single bond CH double bond CH2 plus NOCl giving us product P. Identify the adduct. So we have given a reaction here and we have to identify the adduct we use in this. So options are A option, in which it is CH3, CH, CH2, and in the second position chlorine is attached, in the third position NO is attached. In the B option we have CH3, CHNO, CH2, Cl. In the third option we have CH3, CH2, CH, ClNO. And in the fourth option we have CH2NO, CH2, CH2, Cl. So these are the four options and you have to identify the correct adduct we use in the given reaction. For the given question, the correct answer is option A. Now, using the concept 15.3.1, NOCl undergo electrophilic addition on alkene as. So, in the given reaction, you can see that NOCl is reacting with the alkene. So, NOCl react with alkene with electrophilic addition reaction. So NOCl first it will dissociates into NO positive plus Cl negative. Then we take our reactant alkene CH3CH double bond CH2 propene, and then we react it with NO positive. Right? This is a slow reaction. What it will form? It will form a carbocation CH3 single bond CH positive single bond CH2 NO. Okay, this is the product or this is the carbocation we formed after the reaction of NO positive, or you can say NOCl and alkene propene. Then the Cl negative we obtain from the NOCl react with this carbocation, and it is a fast reaction because we have already a carbocation and we are reacting a electrophile. We are attacking with the electrophile on this in this carbocation, so it will be a fast reaction, and the product form will be CH3 single bond CH single bond Cl single bond CH2 single bond NO. This will be the product we obtain after the reaction, right? So you can see that this is 3-chain propane compound and 3-carbon propane compound, and at the second carbon we have chlorine, at the third carbon we have NO, right? So this will be the final product, and thus the correct answer is option A. Cyclohexene is best prepared from cyclohexanol by which of the following? So when you prepare cyclohexene from cyclohexanol, it is best prepared by which of the following catalyst given in the options? Options are concentrated H3PO4, concentrated HCl or zinc chloride, concentrated hydrochloric acid, or concentrated hydroboric acid. So for the given question, the correct answer is option A, that is concentrated H3PO4. So using the concept 15.5.6, cyclohexanol on treatment with the concentrated H3PO4 undergo acid catalyzed dehydration, which is beta elimination reaction, giving cyclohexene. So when you prepare the cyclohexene from cyclohexanol, what you do? You do the treatment of cyclohexanol with concentrated H3PO4 first, and then it will undergo acid catalyzed dehydration reaction because we are involving acid, and also beta elimination will happen, and it will give us finally cyclohexene. So alcohol convert to alkene. Cyclohexanol reacting with concentrated H3PO4, the water molecule will comes out and beta elimination will happen after the acid catalyzed dehydration, and we get our final product as cyclohexene. Okay, so what we used concentrated H3PO4 for this conversion of cyclohexanol into cyclohexene, and thus our correct answer is option A. 2-phenyl propene on acidic hydration gives what? So this is a compound 2-phenyl propene. When you do acidic hydration of this, what it will give? Options are 2-phenyl 2-propanol, 2-phenyl 1-propanol, 3-phenyl 1-propanol, or 1-phenyl 2-propanol. So for the given question, the correct answer is option A, that is 2-phenyl 2-propanol. Reaction proceeds through carbocation intermediate. So the reaction we have asked about is 2-phenyl propene on acidic hydration. So when this acidic hydration of this given reactant happen, it will proceed through the carbocation intermediate. So we take 2-phenyl propene. 2-phenyl propene means at the second position we have phenyl group attached, and the main chain, the straight chain or the parent chain is propene. We do the acidic hydration of this reactant. This is a slow process. It will give us a carbocation, which is CH3 single bond C positive, at which phenyl group is attached, and single bond CH3. So this is a tertiary carbocation we obtained, and this is also a resonance stabilized carbocation because of the phenyl group present. Benzyl carbocation, you can say it. Okay, and this is benzyl carbocation, we can call it, and we obtained this. And after that, what will happen? We react it with the water molecule. It is a fast reaction, and it will convert to a phenol, which is CH3 single bond C single bond CH3, and at the second position we have hydroxide group and phenyl group. So 2-phenyl 2-propanol, right? So this will be the final product we obtain when you do the acidic hydration of 2-phenyl propene. Thus our correct answer is option A. In the presence of peroxide, hydrogen chloride and hydrogen iodide do not give anti-Markovnikov's addition to alkenes. Because of which reason? So we have given the question that in the presence of peroxides, the hydrogen chloride and hydrogen iodide do not undergo or do not give anti-Markovnikov's addition to alkenes. Why? Options are: both are highly ionic, one is oxidizing and the other is reducing, one of the steps is endothermic in both the cases, or all the steps are exothermic in both the cases. So, for the given question, the correct answer is option C, that is, one of the steps is endothermic in both the cases. Using concept 15.4, in the addition of HBr to the alkene in the presence of peroxide, both the propagation steps are exothermic. So, what is the observation? That when you add HBr to the alkene molecule in the presence of peroxide, the both propagation steps are exothermic. So, ROOR, this is peroxide. Heat kiya, you will heat it and it will convert to 2RO, free radical. Then the HBr will react with this free radical obtained and form a alcohol, ROH, plus Br free radical we will obtain. Then the propagation will happen and CH3 CH double bond CH2, which is propene, then react with this free radical, we obtain bromine free radical, and it will form CH3 single bond CH dot single bond CH2Br. Okay, this is again formed what? Uh, Bromine propyl free radical, right? For this process, the del H value is less than 0. Now, this bromide propyl free radical we obtain react with the HBr we have, and it will convert to a molecule CH3 CH2 CH2Br, propyl bromide, right? And the bromine free radical again will get out of this process, and for this process again the del H is less than 0. Okay, so you can see that when you are adding HBr to the alkene in the presence of peroxide, the steps that are happening, or the two main steps in the propagation under the propagation step, both are exothermic. Del H is less than 0 for both the reactions, for both these steps under the propagation, right? In case of addition of HCl and HI, hydrogen chloride and hydrogen iodide, one of the propagation step is endothermic and the reaction fails to occur. So why the hydrogen chloride and hydrogen iodide do not give anti-Markovnikov's addition with alkene? Because in the under the propagation, two steps will be happen, but one of the step will be going to endothermic in the case of HCl and HI, and that is why the reaction will fails to occur. Thus, the correct region or the correct answer is given in option C. Okay, the reaction of propene with HOCl proceeds via addition of what? So when you react propene alkene with the HOCl molecule, it will proceed via the addition of which substance or atom? Options are H positive in the first step, Cl positive in the first step, OH negative in the first step, or Cl positive and OH negative single step. For the given question, the correct answer is option B, that is Cl positive in the first step. Using the concept 15.3.1, HOCl dissociates into OH minus and Cl plus. And then the propene we take CH3 CH double bond CH2, and it will react with Cl positive we obtain from HOCl. This will be a slow reaction and form a this intermediate, which is CH3 single bond CH single bond CH2, and this structure will formed with the Cl positive. Now what will happen? The OH minus we obtain from HOCl, then this will react with this intermediate we obtained, and this will be a fast reaction, and it will form this molecule CH3 single bond CH single bond CH2 single bond Cl, and at the second position we have hydroxide group attached. So this will be the final product we obtain after the reaction of propene with the HOCl. So it is proceeding with the addition of what? That is, reaction is initiated by Cl positive. You can see that chloronium ion electrophile initiates the reaction of propene and forms a product. That is why we have the correct answer as option B, that Cl positive in the first step. Let's move on to the next one. Which one of the following alkenes will react fastest with H2 under catalytic hydrogenation condition? So we have given some alkenes in the option, and the question is that which alkene react fastest with the hydrogen molecule under the catalytic hydrogenation addition or condition. Options are, in the first option we have alkene, right? You can say this is a butene, right? And the double bond is present between the second and third carbon. In the B option we have again butene, where two R groups are attached to the first carbon. And in the third option we have again a butene, where two R groups are attached with the first carbon and one R group is attached to the second carbon. And we have option D, in which again we have a larger group. So basically at the first carbon we have two R groups, and at the second carbon we have again two carbons attached. Okay, this is also alkene. So all the options we have are alkene, whether it is butane or something else, but the number of R and hydrogen are changing and their position is also changing in all the options, right? So you have to tell that after looking the conformation and the arrangement, which alkene will react fastest with the hydrogen molecule. So for the given question, the correct answer is option A. That means, so the rate of catalytic hydrogenation. Okay, basically we have to perform the reaction between hydrogen and alkene under the catalytic hydrogenation condition. So the rate of catalytic hydrogenation is inversely proportional to stability of alkene. That means if the stability will be higher, the rate of catalytic hydrogenation will be lower. It is also inversely proportional to the number of alkyl substituents with sp2 carbon. That means higher the number of alkyl substituents having the sp2 hybridization, lower will be the rate. And also the rate will be inversely proportional to hyperconjugative of C double bond C with the R groups. Therefore, in the given situation, dia-substituted alkene reacts with or reacts at faster rate than the tri and tetra-substituted alkenes. The stability order is most stable is D, then in C, then in B, and then in A. So A, B, C, and D are representing options, which is given. Okay, which is alkenes, nothing but alkenes, right? So most stable. So the A option alkene will react fastest with the hydrogen molecule under the catalytic hydrogenation condition, right? So after using all this concept, we conclude that the alkene given in the option A will be our correct answer because it will react fastest with the hydrogen. Which one of the following has the smallest heat of hydrogenation per mole? From the options, we have to tell that which one is having the smallest heat of hydrogenation if you count at per mole. Options are 1-butene, trans-2-butene, cis-2-butene, or 1,3-butadiene. So for the given question, the correct answer is option B, that is trans-2-butene. Among the alkenes, heat of hydrogenation depends on greater the number of double bonds, greater is the amount of heat evolved in the hydrogenation. So the heat of hydrogenation among the alkenes will first of all depends upon the number of double bond. Higher will be the double bond, higher will be the heat evolved in hydrogenation of that alkene. Hence, 1,3-butadiene has highest heat of hydrogenation among the given options. So, greater the relative stability of alkenes, greater the relative term is important. Greater the relative stability of alkenes, smaller is the heat evolved in the hydrogenation, and thus trans-2-butene is the most stable among the three given butenes, and hence it will be having least heat of hydrogenation. Okay, so as the stability will be increasing for the alkenes, the heat evolved in the hydrogen will be decreasing, and the most stable among the given butene is trans-2-butene. That is why it will be having the least or smallest heat of hydrogenation per mole, and that is why our correct answer is option B. Bayer's reagent is, options are alkaline permanganate solution, acidified permanganate solution, neutral permanganate solution, or aqueous bromine solution. So, for the given question, The correct answer is option A, that is alkaline permanganate solution. So Bayer's reagent is a cold, dilute, alkaline permanganate solution which is used to detect the presence of olefinic bonds. Okay, this is used to detect the olefinic or the presence of olefinic bonds. Olefinic means the double bonds. So Bayer's reagent is nothing but alkaline permanganate solution.